It's either this class or the other class. I don't remember, but here we go. So, once you understand the rule involving natural log of x, we want to try to apply that rule. So I think you'll see number 5 here kind of goes with what we saw in the video. It says d dx of ln of 3x squared plus 9. And so this is that rule. Simply you recognize that it's natural log, and you say, all right, well, the derivative of natural log is just 1 over the input, whatever it is, times the derivative of that input. So any thoughts? What do you think? Go ahead, Drew.
1 over 3x squared plus 9 times 6x.
Yep.
Oh, okay. I was on number 6. I was so confused.
Sorry, yeah, we're on number 5. And then, of course, if you wanted to take it one step further, or if you just wanted to write it like this at the start, you could write 6x over 3x squared plus 9. Oops, there we go. Dixon, your question?
Yeah, no, you clarified. I was just wondering if you had to write the 1 over step.
No, you could just go straight to that. And of course, you guys can probably see that that fraction that I've written is not in lowest terms. On a free response scenario, I don't care, you know. You can all divide everything through by 3, right? That's not the thing. But just so you know, on a multiple choice scenario, everything's usually like neatened up and cleaned up as much as possible. So you'd probably see it reduced there. So just be aware that you could do it 100% correct and still need to reduce it to match it up to your answer that you would choose. So, okay, Drew, thank you. Nice job. 6, 7, 8, they tangle things up just a little bit more, you know. So if you were going to do a problem like number 6, what would you do before you even really thought about doing any calculus? So we do a little rewrite. Yep. So it'd be, come on. There we go. D dx. And then I'd put some parentheses in there for sure. And I'd go ln of x, the whole thing to the 1/2 power. Make sense? We've done that a lot. We'll continue to do that. All right, so if I were to ask you kind of like, what is the big principle, like what is the big rule, the overall rule for number 6, what would you say?
I would say power rule.
It's chain. No, yeah, sort of indirectly like a general power rule. Yeah, so it's really a chain rule because don't you have a function put inside of another function? And so the ln thing is sort of like a minor detail in this one, right? In number 5, the ln was the thing, right? That was the main focus. But in this one, it's really like a chain rule. And oh, by the way, there's an ln in there, right? So just like we've done before, this doesn't change anything. We do the derivative of the outside, like we open the big box. We see that there's a little box in there, and then we open the little box. So anyone want to venture a shot at this one here? Go ahead, Ben.
1/2 parentheses ln x to the negative 1/2 times 1 over x.
Fantastically done. Perfect. We can clean that up a little bit. We could do some flipping with the negative exponent, get some fractions together. Again, multiple choice scenario, probably would want to do that. For your response, we're done. We found the derivative. We're done. Okay. Any questions on that one? He did a real nice job of just chaining it together, the two pieces in the chain rule there. Do you have any questions? Hallie, anything? I'm trying to read faces. No, Hallie, you're good? All right. Number 7. Number 7 like takes it to another level on the boxes or the tangling of things up, right? There's more than 2 boxes. Looks like to me there's 3 boxes, right? So once again, it's a pretty big chain rule scenario. So if you would, try number 7. We'll let you guys kind of sort through this a little bit, and then we'll check your answers in a minute. Like I said, it's 3 boxes kind of nested together. Any offers on what you think? Anybody want to give it a shot? It's a free shot. No rights or wrongs here that are going to hurt you. John, go ahead.
1 over ln of x squared
1 over ln of x squared
times 1 over x squared times 2x.
times 2x. Okay. Clearly said, hopefully clearly written. What do you guys think? Thumbs up and uh-huhs and yeses. Yeah, you're all right that are agreeing with him. It's definitely correct. So the input for ln is this, and so his first piece of the chain is going to be 1 over that. And of course, that in and of itself is a composite. And so for that, the input is x squared, and so his next chain is going to be 1 over that. And then of course, that is a non-trivial function as well, so times 2x is the final piece in the chain. Obviously, there's some simplifying you could do. I'm not too stressed about it. I know you guys can cancel x's and multiply fractions together. Any questions? You want to see anything else done? Any other reasons for what John did there? Nobody wants to question John? Okay, fair enough. All right, we got a few more to go here, and we'll be done with 5.1. Oh, yeah, go ahead.
How would you combine, like, if this was a multiple choice and like you
Yeah.
wanted a smaller, like just one?
Like a simplified
Yeah, how would
version?
it look
Sure.
like?
So it could look like this. Of course, this is 2x over 1, right? So you get the numerator with the x and the x squared. So you could cancel this x with one of those, leaving you with just an x down there. And then you could just multiply all your numerators together and all of your denominators together. So, 1 times 1 times 2 is just 2. And then down below, you multiply all your denominators together. And so it would be, x times 1 is x, so it'd just be like x ln of x squared. I don't see why you do anything different than that. You got all the positive exponents. There's nothing else that could be canceled. I'd say that's probably the most simple version you could have.
Okay. Why wouldn't it be ln of x cubed? Wouldn't you add the 1 and the 2 of the x's?
No.
Okay. I see.
So x times x squared is x cubed, but x times ln of x squared,
Okay, yeah.
it's not. All right, good question. Anybody else? Okay, you're picking it up okay. It's good stuff. Let's take a look at our final couple of... what I would say with 8 is let's only use our calculators at the last possible second. It's not, normally, obviously a quiz, I'm not going to say that, right? Because what does that really mean? Let's think big concept, and let's only use our calculators when we absolutely, desperately kind of have to. Okay? So number 8 says, if an object has a velocity v of t equals cosine of t times ln of t, is the object's speed increasing or decreasing when t equals 3? So is speed increasing or decreasing at t equals 3? So let's think big picture here. Because isn't it clear, the ln thing is just a minor detail within this question. Even though it's new for us, the bigger concept is something else. So how do we decide? You guys remember, how do you decide whether speed is either increasing or decreasing? Speed being the key word, Dixon?
Whether velocity and acceleration go in the same direction.
Yeah.
Signs agree.
Yeah, whether the signs agree or disagree. That's exactly right. Okay, so if we were trying to decide, are the signs of velocity and acceleration the same or different, we need to look and see what we have, right? Of those two things, what do I have?
Velocity.
So how am I supposed to figure out acceleration when all I have is velocity?
Derivative.
Derivative. Yep. So I'm going to do v prime of t, and what happy little thing has like wormed its way into our problem when we think about v prime of t?
Product.
The product rule, right? You see it? Something times something. You can do the derivative of that. I even put the little dot in there, right? So to make it a little more obvious. It is a product rule. So let's go through that product rule. It's 1d2 plus 2d1. Annie, what do you think? Can you do maybe part of that? 1d2 maybe? Something like that?
Yeah, cosine of t times 1 over x, or t.
Sure, yeah. 1d2. Nicely done. So there's 1d2. Lauren, can you do the other part, the 2d1?
ln of t times negative sine of t.
Yep, nicely done. Okay, so that is our equation for acceleration. It's all well and good, but we want to figure out what's happening at 3, right? So this is probably where we need to get the calculator out. And so we need to figure out what v of 3 is, and we need to figure out what v prime of 3 is. So use your calculators to figure those things out, and then we can make our conclusion at the end. Either v prime of 3 or v of 3.
Derivative, I guess, negative 0.485.
Negative 0.485. And what'd you get for v of 3?
Negative 1.09.
090?
Oh,
It's 08.
087. Okay, I'll go with that. 087. All right, just for the 3 decimal thing. All right, so did you guys agree with his numbers?
yeah.
We do agree with that? Okay, so both of those are negatives, right? The acceleration and velocity at 3 are both negatives. So what's your conclusion?
Speed is increasing.
Speed is increasing. So you just put a big old therefore triangle. Speed is increasing. You can say they're both negative. You know, if you want to say, hey, you know, both acceleration and speed are negative, therefore speed is increasing. You know, tie it all together would be a good thing. Okay, so a little application of what we've done in the past, but just in light of newer things. Good? Okay, the final thing here in section 5.1 is kind of a curious notation, something that's like kind of unique with LN. If I'm going to erase this here in a second, so just watch this. Please don't feel like you need to write it down unless you want to sort of squeeze it into the notes page there. I'm going to, like I said, I'll get rid of this in a second. So the graph of natural log of x. Do you remember it? Have you seen?
Yeah, it goes like, it's like a U almost.
Sort of, yeah. Oops, let's try that again. It looks something like that, right? So natural log is only defined for positive numbers, right? You cannot do the natural log of negative anything, and you can't do the natural log of 0 simply because you'd be asking an impossible question. You can't raise a positive base to any power and get a negative number or 0. And so in certain situations, this causes us a little bit of a problem because we're going to, pardon, it's not a pun really, but we're going to naturally end up trying to plug negatives into like something involving a natural log. And so there is a way around it, and the way around it is to use absolute values. So let me draw that graph. What would you think if I graphed this natural log of absolute value of x? What would you think that graph would look like? It would cover a lot more territory, wouldn't it?
Yeah.
But I think we could describe it very specifically. I don't know, any...
It would just be that one, but like reflected.
Yeah, it's a reflection, yeah. So it would include this, so like this would still be involved, but then it would also be this side over here. So when you think about natural log of absolute value of x, now there's only one number you can't plug in. 0. You got a vertical asymptote at 0 for something like that. So this just opened up the whole left side of the graph of numbers that could possibly be plugged in. So then, bless you, the question then maybe is, how does this work with calculus? Let me show you how this works. Let me erase all that. There we go. So if you had something like number 9, I'm going to just give you the answer straight up, and then I'll, if needed or if wanted, maybe I'll just do it anyway, so kind of explain why. So it says f of x equals ln of cosine of x. The answer to this is pretty simple based on what you've been doing. We would simply do this. We'd say 1 over cosine of x. Notice I've dropped the absolute values. That's significant, right? Normally you can't just drop stuff, and if you want, I'll show you why. And then of course you'd multiply by the derivative of what you plugged in, or what was the inside, and so the derivative of cosine,
Positives. Oh, derivative, yeah.
derivative, yeah, gives you negative sign. So times negative sine of x. And let's call upon your old trig identity skills. What is it?
Negative tangent.
Yes, negative tangent. There you go. So negative tangent of x. And that would just be the answer right there. And if you did the trig identity or not, it really doesn't matter. But that'd be your final answer. So I want to point out again that like the absolute values were there, and I just sort of like ignored them. They just disappeared. Can I explain why? Okay, so here's how this works. You probably saw this in a pre-calc class somewhere along the line. We've talked about it briefly in here. Whenever you have absolute values, essentially what absolute values do is they create a piecewise graph. 2 pieces, 3 pieces, 4 pieces, who knows how many pieces, but essentially the pieces are made up of these things. Parts of the graph that were affected by the absolute values and parts of the graph that were not affected, right? So if the original graph had some negative y values, those parts would be affected by the absolute values. If the original graph has parts that had only positive values, those parts would not be affected at all because, of course, the absolute value of a positive is still a positive. That make sense? So here's what we could do. If I was going to write f of x, if I was going to rewrite this as a piecewise graph, or a piecewise function, it would look like this. F of x would equal ln of cosine of x if cosine of x is positive. So in other words, if cosine of x is positive, there's no change whatsoever. You just drop the absolute values. However, if cosine of x is negative, it would change things a little bit, right? Because how do you take something that's negative and turn it into a positive?
Multiply by a negative.
Multiply by a negative, -1 or whatever, yeah. So it would be ln of negative cosine of x, if cosine was negative. So it creates this piecewise, two parts here. Well, I mean, I guess it is cosine, so it's probably a lot more than two parts if you consider the whole domain, but whatever, two main parts. So let's take that now, and let's do the derivative. And again, let's base the derivative on what we have done just in the last few minutes, as well as from the video. So I'm going to write f prime equals, let's do the first part. So if if cosine of x is positive. Okay, so what do you think? ln of cosine of x, the derivative would be what? Yeah, it'd be 1. I'll do the two parts here, but you're right, of course, John. It'd be 1 over cosine times negative sine of x, which would lead to the negative tangent. We already talked about that, right? That's not exactly earth-shattering. The other one, let's think about how this would work. Wouldn't the other one be 1 over negative cosine of x? Right? So you might think, oh, it's different. It's not like you said, but think about this. What is the derivative of negative cosine? Positive sine, right? And so sine of x would be the chain rule part. And so no matter which side of it you look at, you're still going to get negative tangent of x. Just one of them, the negative was in the bottom, the other one was in the top. It's the same thing, right? So if you ever do encounter something like this, you're supposed to do the derivative. You can essentially proceed forward. If you're just doing what's the derivative, you can proceed forward as if the absolute values aren't even there.
Is that only for cosine or like?
Nope, that would work with really any input, I think.
Even sine? Because,
Yeah.
okay.
Even if there's not like a trig function with it? Like
Y-
even if it's
yeah.
not sine or cosine, if it's just like,
Even if it was just x. If it was just x.
Cancel out.
Yeah.
Sines would cancel out, that's what-
Because the signs
would cancel.
interact in the same way either way. Yep, exactly. Yeah, so yeah, if you just had x, then you'd get 1 over x for one of them, and you'd get -1 over negative x for the other, and they would still cancel out. So the signs will, in the end, cancel out as needed to get the same thing as the other one. So anyway, that's that. That's 5.1, and